Alrighty, let's go ahead and talk about this homework. So we're going to do a conversion of tons, yards cubed into grams per centimeter cubed. So we talked about this unit on Tuesday. What was this unit used for?
Digging dirt.
Yeah, mining. So they're going to dig a huge yard by yard chunk of dirt and then measure its mass in terms of tons. And so what does this measure? What? Density. It measures density. So when you've got a mass over a volume, that's measuring density. And what was our little brief definition of that density thing? The easy, like, no-brainer definition. Don't have to think about it.
How compact stuff is.
How compact that thing is, right there. That thing's compact, that thing's dense. Okay, so we're gonna switch this 2.34 tons over yards cubed. So I'm just gonna do the tons one first. 1 ton, 2,000 pounds. So the ton cancels out. And then it's 2.2 pounds for 1 kilogram. And then the pounds cancels out. And then it's 1 kilogram is 1,000 grams. And the kilograms cancel out. And so I've got half of my problem done. I've got the grams unit in the numerator where I want it. So now I need to take that yards cubed and get it over into centimeters cubed. So far I've just been putting a unit in the denominator and being able to cancel it directly out with something in the numerator. Right now I've got 3 units in the denominator and I'd like to get rid of them. So I can either do it like this. I can either go 1 yard is, I don't know, we'll say 3 feet. So if I use that unit conversion, what happens?
You're still left with that square.
Yeah, this yard here cancels out with one of these yards, but it's still yards squared. Everybody okay with that? Because what's the exponent that's over this yard here on the end? A 1. So that 1 in the numerator cancels out with one of the 1s in the denominator. When you've got exponents and you're dividing the same quantity, what happens to the exponents? What do they do to each other? The denominator subtracts off the numerator, and if they're multiplying together the same number, then I just add them. So 5 to the second plus, or times 5 to the third is 5 to the fifth, just adding them up. So something else I could do is, what if instead of me just putting 1 yard right here, I put 3 of them there? So when I say I put 3 of them there, I put 3 of them there. Not times 3, but 3 cubed. Cubing it, sorry. The issue is, when I do that, this is no longer equal, right? The numerator and the denominator aren't equal anymore. But I can make them equal. If I cube this thing, I have to cube this 1, I have to cube this foot, and I have to cube this 3. Because cubing it means that I'm doing it 3 times, right? So what I've done is I've put that same unit conversion up top 3 times. So it's 1 yard per 3 feet, 1 yard, 3 feet, 1 yard, 3 feet. So this little thing that I wrote over here is the same as this 1 unit conversion. And what I have are 3 yards in the numerator, which could cancel out with the 3 yards here in the very first thing that I wrote. Or I could just take this yard and this yard and this yard and say it's yards cubed, and this 1 and this 1 and this 1 and say it's 1 cubed, and this 3 and this 3 and this 3 and say it's 3 cubed, and so forth. So I'm just going to get rid of all that. So what I was able to do is cancel out all 3 yard units at once. I've got feet cubed down here. I don't really want feet cubed. I want centimeters cubed. So I'm going to go with, I need feet cubed up here, and then the unit for this is gonna be, conversion for this is gonna be 12 inches, and then 1. But since it's cubed, I gotta do it 3 times again. And I'm gonna do this one more time, inches cubed, and then it'll be 2.54 centimeters cubed, cubed, and cubed. So if you do one of these where you cube something in the unit conversion, you need to cube everything in the unit conversion. And so now I've got feet cubed canceling out with feet cubed, and inches cubed canceling out with inches cubed, and I should be happy that now I've got grams and I've got centimeters cubed left. And that's all I wanted, and that's all that's left as far as units go. So then I have to throw this into the calculator. So I got 2.34 times 2,000 times 1,000 divided by 2.2 divided by 3 cubed divided by 12 cubed and divided by 2.54 cubed. And it looks like 2.78 grams per centimeter cubed. We good with that? Do we want to talk about any of the steps that I did in this one? Go for it.
So, the book tells us that grams is like 4.56 or something like that, per pound, grams per pound. So could
Did
we
you say
do that?
400?
Oh, 400, yes.
Okay,
400.
yeah, that would be fine, totally.
Could have done it that way.
Absolutely, for sure. Hopefully you got the same number.
The cubing.
Okay.
I have a way cubing, but I took.
Do we, are we okay with the cubing part?
What's difficult for me is understanding, like, so you got it to grams, and then you just kind of like hooked up with yards square, or yards cubed. And how do you know which one goes on the top?
What were we looking for in this problem?
Centimeters cubed.
Nope.
Grams.
Grams per. So what does this word mean in math? That means everything after the per is in the denominator, right? So I'm starting off with the number that is I'm starting off with a number that's 2.34. Wait, was that right? Tons per yard cubed. Okay, so what we're saying is if I had 2.34 tons, what else do I know about this stuff? Say again?
For every yard cube.
For if I had a yard cube, so let's say this is a yardstick and not a meter stick. So I'm talking about a box that's this tall and this wide and this long. So if I had a box that was that big, this substance would have a mass of 2.34 tons. Okay? So how many of those boxes did I have? It's just one, right? If I had one of those boxes, it's that ton. So this number 1 can be put down there. Nobody ever puts it down there because why? It's understood and it doesn't come into play mathematically because it's just a 1. So is it totally okay for me to write 1 yard cube divided by 2.34 tons?
We were looking for something else.
Nope, it's totally fine. What was this definition? What is this telling me?
There's one
if I had 2.34 tons, it would do what? It would take up a box that was a yard on all sides, right? Now what we're saying is I got the same stuff, somebody just gave me a yard cube of this box. Tell me what its mass is. Yeah, it doesn't matter which direction you put it. So I don't care what you put in the numerator or denominator in the railroad track thing, except in the problem, it wanted an answer given in what? Grams per centimeter cubed. So what that tells you is, in the numerator, there better be a number with a unit that I can convert that unit into grams. And there better be a number with a unit that I can convert into centimeters cubed. So what we were saying is I needed a mass unit in the numerator and a volume unit in the denominator. I don't care which ones I use because I could eventually convert into the ones I want. But that's how I needed to be set up. So for this one here, I started off with that tons in the numerator and yards cubed in the denominator because when I'm finished, I wanted this mass number here, this grams, up top and the centimeter cubed in the bottom. So that was the only way I could put it in to get the answer I want. If I had accidentally put it in upside down, what would happen? I would get a number with a unit of centimeters cubed on the top, grams on the bottom, and this number wouldn't be 2.17, it would be what? It would be 1 divided by 2.78. So then I would just have to flip the thing over. So if you did it upside down, all right, well, don't do that again, but then you can just invert the number. I'm not sure if I was answering your question or not, Ashley. Good? Okay.
So after we have it all like that, we multiply everything across.
Yeah.
And then everything on the bottom.
So there's two ways you can do this. There's a fast way and I guess you could say a pretty way, especially if you're using like a TI-89 calculator. If you're just using a regular calculator, let's just talk about this mathematically. Everything these are all fractions, right? These are all fractions multiplied by each other. The way that you normally see this written out is it would be 2.34 tons divided by 1 yard cubed times, and then 2,000 lb divided by 1 ton. That's the way it's normally written. That just takes more time to write it, so I've been writing it like this since high school. So what we were doing here is, this is a numerator, these things are all numerators, and these things are all denominators. So it doesn't matter how you type it into your calculator, as long as everything up here is multiply and everything down here divides all of those multiplies. So the two ways you can do it, the way I do it is I just type this number times this number times this number, and then I hit divided by this number. What am I doing with this 3 to the cube? Is it multiplied or divided? I'm still dividing. This is still in the denominator, so I just hit the divide button again. Because every time you hit a multiply or a divide, as the calculator is going through, what does it do after each one of those? And then there's a number there, there's an answer, right? It's equals. Were you okay with that? So when I type in 2.34 times 2,000 times 1,000, the calculator sees this, multiplies by 2,000, and then equals whatever this answer is, then multiplies by 1,000. Okay? So if I type these three things in, multiply, and then I type in divide 2.21, it takes this, what I had here, multiplies by 1,000, then divides by 2.1, then hits equals. And then it's okay for me to hit divide 3 cubed. We all right with that? So when you do that, if you do that in the calculator in that fashion, it doesn't look very pretty, but it's quicker. But I don't know if you can see it. There's divide on that. So it doesn't look like it looks here. I can make it look like it looks here, but what would I have to do? Say again?
Parentheses.
Add parentheses. So if in the calculator I wanted it to look exactly like it looks here, I could type this in, then type divide, then a parentheses, and then type 2.21 times 3 cubed times 12 cubed times 2.54 cubed, close the parentheses. And then it'll take this whole thing and put it underneath this thing, and it'll actually show in the calculator these things in the numerator, and then it'll put these things in the denominator. If you're wondering if you've typed it in correctly, if you type it in like that, then it's like, oh yeah, that 2.54 cubed is in the denominator where it's supposed to be. So it'll take you 2 extra keystrokes and remembering that you hit multiply, but it doesn't matter how you type it in, which way you do it. If you want, you can just be silly about it, and I mean, it's not really silly. You could type this number and then times this number divided by this number times this number divided by. It's still going to work, because after each one of these operations, it hits equals. The order of operations doesn't matter for multiplication and division. Okay? All right. Problems that have addition and subtraction mixed with multiplication and division are the only problems that you can't use the railroad track method for. It just doesn't work. So you actually need an equation if we're going to do a conversion like that. The only one that we're going to use that's going to be a requirement is this one. This is the only one when I'm swapping back and forth between Celsius and Fahrenheit and Kelvin and whatnot. Okay, so rearrange this to solve for temperature final. Okay, so I need to multiply both sides by 9 and divide both sides by 5. So 9/5 here, those cancel out, and then it's 9/5 over here. Okay, so I get 9/5 times temperature Celsius equals temperature Fahrenheit minus 32. So I'll add 32 here, that'll cancel, then I'll add 32 here. So I'll get temperature final is equal to 9/5 times temperature Celsius plus 32. Okay with that? I'm going to put this equation on the test, but if you want a way to remember it, body temp in Celsius is what temperature? 37 degrees Celsius. And in Fahrenheit, body temp is? So the Fahrenheit number is bigger, right? So when I'm doing this, when I'm taking this Celsius number right here, and I'm going to convert this guy into Fahrenheit, the number is going to be bigger. Okay? So this right here, multiplying something by 9/5 makes the number bigger, right? And then adding 32 to it obviously makes the number bigger. So these two things happen to make the number larger. When I'm going to the Celsius side, let's look at this equation over here. I've got a temperature Fahrenheit, and what do I need to do to my Fahrenheit number to make it a Celsius number? Make it smaller. So what do? I subtract a number off of it, and then I multiply it by 5/9, which makes it even smaller. Then the only thing you gotta remember is, do I subtract first or do I multiply first? Okay with that? So when I'm doing the Fahrenheit one, I do when I have the Celsius number, I multiply it first. And when I have the Fahrenheit number, I have to subtract first. And you do have to make sure you put this into the calculator correctly. So let's talk about these parentheses right here. Those are the only parentheses that matter. Why? I need to make sure that before I multiply by 5 divided by 9, that I subtract off the 32. Because if I type this, that equation there in without these two parentheses, tell me what's going to happen.
It's gonna do all the multiplications.
Yeah, it's going to take 32, multiply it by 5, then divide it by 9, then subtract that number off of temperature Fahrenheit. That will not be the correct number. But hopefully if you did that by accident, that you realize that the number's not correct, because you should know 3 Celsius numbers. What are the 3 Celsius numbers? 0, 37, and 100. And if you know those 3, then you could look at this problem and say, oh, that doesn't make any sense. because that temperature Celsius is higher than normal body temperature in Fahrenheit. So I must have done the calculation wrong. All right, so we're going to convert 100 degrees Fahrenheit into degrees Celsius in Kelvin. Or when we're doing this, that's 100 degrees Fahrenheit. So what Celsius temperature approximately should you expect?
37.
98.6 is pretty close to 100, right? So we're pretty close to 37. So something, maybe 38, 37.9, something like that. So before you do these problems, you should ask yourself, what am I expecting to see? And then you'll verify your answer before you actually ever do it. So we're going to take the Fahrenheit, and we're going to subtract off 32, and then we're going to multiply by 5/9. So 68 times 5 divided by 9. What is that? $37.77 just repeats degrees Celsius. Okay, what do I get to report for my degrees Celsius answer? 4 sig figs. Why? Because there's a 100 with a decimal place and another 0. Why would somebody ever write the 0 after the decimal place? When the thing that they're reading actually says 0, right? Does that make sense? I never would write a 0 after a decimal place unless I'm looking at something that's saying that. And then it actually is meaningful. So here I've got 37.78 degrees Celsius. That's just the answer for degrees Celsius. We don't do that sig fig thing until the very end, so I'm not going to use that answer to calculate out my Kelvin number. I'm going to use this that I've already got. So then I'll just add, I'll add 273 to this, and I'll get 310.778 Kelvin. And so we'll say it's 310.8 Kelvin. So there are my two answers. Do you notice that the degree symbol isn't attached to the Kelvin number? Does anybody have any idea why? The Kelvin temperature is the temperature, and the other, the Fahrenheit and the Celsius, they're degrees of the temperature. They're not the actual true scientific temperature, where the Kelvin one is. Now we're going to convert Kelvin into Celsius and then into Fahrenheit. So I'm going to go ahead and subtract off 273 and get 17. All right? Yeah. So that'll be degrees Celsius. And that's also my answer for this one, for the degrees Celsius. Why? I mean significant figure-wise. How many sig figs did I start with this time? Just 2, right? There's no decimal place after that 0, so I'm going to go ahead and say that it's 2 sig figs, so my answer for this is going to be 17 degrees Celsius. So now that I know that it's 17 degrees Celsius, what kind of Fahrenheit temp would you expect? '70s, '60s, somewhere around there, right? Because 32 Fahrenheit is freezing and 0 Celsius is freezing, and 98.6 is body temp and 37, so somewhere falling in between there. So I'm going to go ahead and add 32 to this and then multiply by 9/5. I can't remember if that's right. Yeah, I think that's right. 17 plus 32 times 9. No, wait, don't do that. Times 9. Yeah, so I know I made a mistake because that my calculator just spit out 88.2, so that's way too high. So I'm gonna have to redo this. So we'll say it's times 9/5 plus 32. So 17 times 9 divided by 5 equals, and then plus 32. That's better. So I got an answer of 62.6 degrees Fahrenheit. So I'm going to report that as 63 degrees Fahrenheit. So I have 2 significant figures. That brief non-scientific definition for density, what do we have?
How much stuff is compacted? Stuff is.
That's pretty non-scientific sounding, right? How compact that stuff is. What's the density of a piece of wood with a mass of 240 grams and a volume of 268 centimeters cubed? Will this float? Okay, so we'll do the calculation for the density, but can we answer this question, the second question, before we do anything?
Yeah.
Since the mass is smaller than the volume, that means whatever this number is going to be less than 1, and since density of water is 1, this is going to have a density less than 1, so then, yeah, it's going to float for sure. When I'm calculating density, what unit do I need? What's the unit for density? It could be gram over centimeter cube, but what I have is a mass unit divided by a volume unit. So in my railroad track, I'm just going to take my mass number, which is 240 grams, and I'm going to divide it by my volume number, which was 268 centimeters cubed. Yep, that is the density equation, density divided, or mass divided by volume, but I'm just setting it up because I remember what the units are for this, this density thing. So what do we get? 240 divided by. So I get 0.89, we'll say 6, but I only have 2 significant figures. We okay with that? Why just 2? The 240, there's only 2, but there's 3 in the 268, so can I use 3? I got to use the worst one. So my answer in this is going to actually end up being 0.90 grams per centimeter cubed. Why? I can only use 2, and it can't be 0.89 because that 6 rounds the 9 up. But I can't just get rid of the second significant figure, so it is 0.90, letting the person know it's significant to that hundredths place. And then, yes. What else we got here? Okay. If you add that many calories to that amount of gram, what's the final temperature going to be if the initial temperature is that? Okay, so what am I trying to calculate?
Final temperature.
I'm trying to calculate a final temperature. I'm trying to calculate a temperature unit. All right, so you needed to look up what the specific heat of glass was. What'd you guys come up with? Okay, so I need a degree C unit. When I put energy into this chunk of glass, what's going to happen to the glass's energy or temperature? It's going to go up. Okay. Does it matter what the initial temperature of the glass was when I put this energy in? So the first question I asked was, if I put energy into it, the temp goes up, right? I don't care what the initial and final temperatures are, I just care that the temp went up. Does it matter what the initial point is?
Your final answer.
I'm just asking about this first part here. Does it matter where the initial is? If I put that many calories into glass that has that mass, the temperature is going to go up this much, right? It doesn't matter if the starting temperature was 10 degrees Fahrenheit or if the starting temperature was 500 degrees Fahrenheit. Its temperature is still going to go up this much. We good with that? Okay, so what I need to do is figure out how much this temperature changed. So I need to figure out an answer that's got a temperature unit, and so I'm going to use the specific heat thing. That's what I'm going to start with. So I'm going to put 0.22 calories per gram degree C.
In the bottom.
I put the 0.22 in the bottom. How come?
Because you need a temperature unit.
I need a temperature unit, and the temperature unit I'm going to use is that one right there. And now the temperature unit is where I want it. It's in the numerator. So now that I have this 0.22 in the denominator with these 3 units, what do I need to do with the units? I need to get rid of that gram unit and I need to get rid of that calorie unit. So I'm gonna get rid of the gram unit by putting in 675 grams in the denominator, and then that gram unit cancels out. And then I'm gonna put in 3750 calories in the numerator, so I can cancel out that calorie unit. And so then I've got 3750 divided by 675 divided by 0.22, and I get 25.25. And the unit on it is degrees C. Okay? What is the significance of that number? What is that number, that 25.25? That's the temperature change of this chunk of glass that had this 3750 calories added to it. Great, so now I know how much it changed. I want to know its final temp. What did it start at? 15. So then all I need to do is add 15 to this, right? And so I'll get 40.25 degrees C. But I only have two significant figures, so then my answer will be 40 with a decimal place right there, degrees C. That fixes the two sig figs.
Have the decimal place though?
Second?
Have the decimal place taken care of that?
Yeah, this 0 right here, definitely use a decimal place because we have 3 sig figs, 3 sig figs, and 2 sig figs. So then my answer, that was my calculated answer, and I can only use 2 of these. So it'll be that one and that one. And if I left no decimal place there, what's that telling the person? That means I didn't know about that 4, but I do. I had 2 sig figs. I put that decimal place there, and that's telling the person I knew both of those for sure.
So you don't actually need to know the equation, you just need to know what is required in the equation. Like you need to know that you need the specific temperature.
I need to know what I'm looking for. And so I just take everything and rearrange it, flip it over, put it however I want to get what I want out.
It is, it's like 3.
Okay. So this is these problems we're talking about kinetic energy. And so this, I looked up these numbers on these vehicles, and so the VW Bug is about half the mass of this pickup truck. So given this first problem, just how the truck's obviously got more energy, right? How much more energy does it have? Twice as much. So what I have is the kinetic energy equation. So that kinetic energy is 1/2 mass velocity squared. So what I have is the VW Bug that's got a 1/2 mv squared, and I have the truck that's 1/2 mv squared. If I'm comparing these two things, what can I do right away?
Throw in mass.
I could, but can't I get rid of the halves? We okay with that? I'm going to compare these two things to each other, and the half is a constant on both sides of the equation. It's sort of like having a times b times c equals b times d. What would you do to this equation? You cancel the b's out right away. So it was okay to cancel out the halves because they're the same for sure. Okay, so this mass and this mass over here, how are they related to each other? By what factor? 1/2, or I'm going to use 2. So I'm going to put a 2 over here. So this is the truck on this side. And I really spelled out that badly. We'll
Can
just,
you cancel out the velocities?
I can. One sec. And then this is the Bug. So the masses are relative to each other because they're, the truck is double the mass of the Bug. But what about those velocities? They're exactly the same value, right? So then I can just get rid of them. So those are gone. So tell me how much more energy the truck has based off of what we've done so far. 2. The only difference between these two equations is this factor of 2. So this truck has twice as much energy as the VW Bug does. All right? You could have thrown all of those numbers into the equation, but you don't need to because I made the numbers nice and easy. Okay, so a different situation is happening here. I'm going to take the same 1/2 mv squared here and 1/2 mv squared here. So this is my truck on this side. And here's my VW bug on this side. So what do I want to do with these equations when I'm comparing them right off the bat?
Cancel out the half.
The halves are gone. Okay. What am I going to do with the masses? I'll go ahead and put a 2 in front of the truck's mass, right? We okay with that? Okay, so I cannot cancel out the velocities this time because they're not the same. So tell me about the velocity of the bug.
It's having about twice as fast.
The truck's half of it, but the VW bug is twice as fast, right? So this velocity number compared to the other velocity number is twice as big. Okay? So I can't just cancel stuff out with this one because that 2 that's in front of the velocity for the VW bug has an exponent that's controlling it. We okay with that? So what does it equate to? A 2 squared gives you what? 4. So over here, this velocity thing is now changed by a factor of 4. Or I didn't modify the velocity on this guy, but I doubled but it's got twice as much mass. So tell me who's got more energy this time. This time the bug, and the bug has twice as much energy. And that last one there, calories definition?
It's the amount of energy it takes to raise 1 gram of water to 1 degree Celsius.
So I raise 1 gram of water 1 degree Celsius. So a very small amount of energy relative to everything we do in a normal day.
So that's those last two that we did.
Yeah.
in the car. We didn't use the railroad just because it was super simple.
We didn't use the railroad just because I wanted you guys to be thinking about how factors affect magnitude as opposed to actual numbers. So the problem before this, remember I didn't care where the temperature started, the initial temperature of that glass. All I was concerned about was how much adding this heat changed the factor, and it didn't change the temperature. It didn't matter what the initial temperature was, it's still going to change it by that amount. So in this problem here, it didn't matter what the actual mass of the two things were, it only mattered what the relative mass is relating to each other.